All right, I'm going to do a little review of central limit theorem in case any of you are stuck from first semester. If you go back and remember the Reese's Pieces, the actual proportion, the parameter p is 0.45. I'm doing a sample size of 25. When we did just the one sample, you selected 25 candies, counted the number of orange, found the proportion, and for example got p hat 0.48 of your 25 candies were orange. Put a dot down below. When we did it in class, you went to the board and put your dot on the board. Someone else does it, gets a sample proportion of 0.52, puts their dot on the board. Now the mean of those two sample proportions is 0.5 with a standard deviation of 0.028. Remember the concept of sampling variability. Just because you're taking the same sample size from the same population doesn't mean you get the same answer every time. If we hopefully remember to take animate off and do that a total of 500 times, you now have the graph that represents the sampling distribution where every dot is a p-hat from a sample of size 25. I did a total of 500 samples, so if you could actually see the dots, there'd be 500. The mean of all my sample proportions is 0.444, which is supposed to be close to the actual proportion of 0.45 because it's not biased, it was random. And the standard deviation was 0.095, and it was pretty close to being a normal curve. Then if you also remember your note sheet from first semester, we just said that the sampling distribution is the graph of all the possible sample proportions. And the central limit theorem tells you what the shape, center, and spread of that sampling distribution will be. You know the approximately normal if and only if, and your conditions were that n times p is at least 10, and n times 1 minus p is at least 10. I'll go back and talk about that. As long as it's not biased, mean of all the sample proportions is equal to the actual proportion, and the standard deviation is that formula with that notation. Now, both of those, this one right here and this one right here, are on your formula sheets with the symbol notation included, so that shouldn't be too hard to remember. Okay, so apply that to the Reese's Pieces. The CLT says the sampling distribution for all the p-hats will be, and I added in there for samples of size 25 from the population. You know approximately normal. And that is where you check that your sample size was big enough. In this case, 25. I expected 45% of them to be orange. So 45% of 25 should be 11.25. That's at least 10, so we're good. And I expect 55%, 1 minus 0.45, to be not orange, which should be 13.75. Again, at least 10. If you add these two numbers together, they have to equal your original sample size, because this is how many you expect to be orange, and this is how many you expect to not be orange. Make sure they're both at least 10. You don't have to write all that extra. I'm just explaining. If that's true, then it's approximately normal. So basically, you just told me n is big enough, right? The center of all those possible samples, even though they vary. So the center of all the p-hats, or better yet, the mean of all the p-hats is equal to 0.45. And the spread, or the standard deviation, please make sure you say standard deviation somewhere, of all the p-hats, or sigma sub p-hat, and that's where you do your formula. Divided by n, which in this case should have been 0.0995. And if you go back and look at our simulation, the actual mean of all of our sample proportions was 0.444, close enough to 0.45, and our standard deviation from the simulation was 0.095, where we just predicted it would be 0.0995. Again, close enough to prove that these formulas are accurate, that they are describing the same graph that's the graph of all the possible sample proportions from that population. Again, everything we're going to do after this is based on this, so I really want the central limit theorem pounded in. Hope this helps when you get stuck.